In the previous videos, we have looked a lot about energy and how energy could be lost. And it's kind of like this Coulomb train model where the battery provides the energy. Look at this golden energy coming out. And then these charges will carry the energy, electrical energy, and give it to whoever needs it, such as a resistor who will take the electrical energy and throw it out as heat. If it's a light bulb, it take the energy, throw it out as light energy and heat energy. But of course, you already know that some people might be stealing energy inside the battery itself, called internal resistance. So, when you measure current, you are seeing how many charges pass by per unit time. When you use a voltmeter to measure potential difference, you say, oh, between here and here, what's the energy difference? Look here, wow, so much golden energy. On the other side, nothing left. That's the main idea of energy conversion in a circuit. Now, what if we have two resistors in parallel with the battery? Wow, this picture's got complicated. So, these charges will split in such a way that they will deliver the same amount of energy to the first resistor and the same amount of energy to the second resistor as well. So traditionally, we would draw our battery to be something like a... Okay, let me just flip the battery. It's easier to think it that way. Battery goes to one resistor, or I guess bulbs. One bulb here and another bulb down here. This is an example of how you would see it normally in a circuit. Oh man, my lines are not the most straight today, but that's it. Okay, so whatever this battery supply, if it's EMF, then EMF, whatever value that is, will be the same across every parallel line. How do you know if they're parallel or not? Well, you got to see how many loops can you make. For example, current can come out and go in. That's one path, one loop. But you can do another loop that goes down and come back to the battery. So you're like, oh, so you can have two train lines like the picture on the left. So that's how you know these two are parallel. The other way to tell is to see the current flow. Current flow, reach a junction. Some current will go here, some current will go down. How much will split? We don't know. We have to do some calculation. So this one will all be E and E. One thing to be careful is that sometimes you may have internal resistance of the battery. Oh no. So let's draw this box here. Okay. So the battery will lose some energy in the first place. Maybe some lost volts. So we cannot say that every light bulb will get E anymore. We have to say, oh, this is a terminal potential difference, including the lost volts. So each light bulb will get that terminal potential difference worth of energy. So V terminal and V terminal. And this V terminal will change depending on the current in the circuit, because like the previous video we mentioned, lost volt depend on current, remember? So V lost depends on current flowing through the battery times the lost volts are internal resistance. So for example, if your current is very small, then the lost volts will decrease. That's the relationship of it. Okay? And number two, to summarize, okay, this is point number one. Ding, ding. Point number two is that your terminal potential difference, better to say terminal instead, because in case got lost volts, equals to V1 and V2. I think I'm just going to say V1 and V2 to illustrate this idea. V1, V2. Okay, parallel across each parallel line is the same. Well, how about if you are in series with a battery? That will look something like this. Battery provides electrical energy. Energy goes, and oh, we have two people, two units, two components that need energy. Resistor 1, resistor 2. So electricity is very cute. It will share the voltage depending on how much each of these resistors use. So for example, the energy come in, it uses some energy, and you see what's coming out is a bit lesser already. Then that remainder energy will go to R2, and by the time you come out R2, there's no more energy to carry. It's all empty already. See this side? No more gold. So once again, these two voltmeters will look at the difference between point C and point D. What's the difference in energy per unit coulomb? Between point E and point F, what's the difference in energy per unit coulomb? That's the whole idea. So we could draw our, how shall we draw this? We can draw something like this. Okay, want to include internal resistance? Sure. Who knows, man? Who knows? There may be internal resistance. And then the battery is connected to 1 resistor and 2 resistor, for example. So energy will be shared. How do we know how much is shared? We can use what we call the ratio. So whatever is provided by the battery, you can call this V terminal. Okay, and each of these resistors will take a bit of that energy provided to them, V1, V2, depending on what their resistance is, R1, R2. The first ratio that you can use when trying to solve any kind of question is you ratio to each other. So ratio to each other. What does that mean? Means V1 and V2. Okay, so we take V1 over V2. What are we ratioing? The resistance. So we ratio that equals to R1 over R2. Simple as that. Okay, this is the first equation that you can use a lot to do kind of ratioing. So what does this mean? Okay, in simple terms, I give you an example. So if you have, let's say, a 50 ohm and a 50 ohm resistor, and if the first resistor has 2 volts, what will the second resistor have? Also 2 volts, because they have the same resistance. They would use the same amount of energy because the current flowing through them is the same. Same. You very hungry, you also very hungry. Okay, I give you same energy. The second question is then, is there another way we can do ratios? Yes, there's one more. What if I give you a situation where you have 50 ohm and the other one is 100 ohm, and you're connected to a battery of EMF, let's give a battery EMF. EMF is 12 volts, for example. Okay, or rather terminal potential difference. Safer to say terminal potential difference. Terminal potential difference given to these two is 12 volts. How would you find V1 and V2? V1, V2. So you see here, we cannot really use the first ratio method already because we don't have enough information. We don't know V1, we don't know V2. We can do R1 over R2, but we wouldn't know for sure. So the second method here is to ratio to the total. I'm going to skip over and write on this side because there's no more space. So ratio to the total across these two in series. What does that mean? So let's say I want to find V1. So V1 over total provided across these two resistors. In this case, it will be the terminal potential difference, which across this whole thing is V total or V terminal, which is 12 volts. My head's blocking a bit. Okay, and then we ratio the resistors as well. But this time we are ratioing R1 to R total. You see that? What you want to find over what is the total, what you want to find over what is the total. So this one, if we try this calculation, okay, we write it out. V1, I don't know what that is, but V1 over 12 equals to 50 over the total. And you should get a V1 of 4 volts. Oh, I just noticed a typo. This should be 100. Why did I write 500? Yeah. 4 volts. Okay. So V1 gets 4 volts. That means V2 will have how much? If you are taking a share of 4, then my other friend only have 8 left. Because 4 plus 8 is 12. That's the ratio happening there. One more thing you can check is the ratio to each other can now be applied. Because if you look at this nice pattern, 50 times how much become 100? 50 times 2. This is times 2. So the ratio there, the proportion is 2. Then the voltage, you see here, also times 2. 4 times 2 is 8. So if you have 2 times the resistance, you need 2 times the voltage. Of course, within whatever is available to all this in series. That's the whole idea of what it means to share the energy with everyone in the same chain. And those two are the formulas generally to tell you the how you can divide up the potential. It's called potential divider. We'll see more about this in the future section, don't worry. Now the question is, so means we can calculate the volts across any of these components. How do we actually find the energy that comes out? Let's say this first light bulb is bright. How do we quantify that? In terms of joules. Energy? In terms of units of joules. Is there an equation for it? Yes. And now we're going to look at that. So power. Based on a previous video where we talked about potential difference, we have this definition of volts, right? Volts is work done per unit charge, Q, or energy converted per unit charge. So that is where we have the tip for energy already. So that means W equals to Q times the potential difference. And for Q, we learned in the earlier video that Q equals to IT. That's the definition of current. So if we sub that into Q, we will have work done equals to VIT. That's work done. Or work done is also known as energy change. So the energy converted or energy dissipated or whatever energy is VIT. This is the very first one to write down. And of course, like all energy, the unit is going to be in what? The unit is in joules. J. Because now it's energy, kinetic energy, GPE, all the energy. Okay, you can use that one. But also, very often, or more commonly in electricity, this is just the amount of energy released. How much energy is released? What's the rate? A lot of energy come out or slowly energy come out? That one, we have to use a second definition, which is power. So power, let's put this number 1. Number 2, power. What's power? What's the power? Remember from the previous chapter? Power is work done over time. Or in other words, the change in energy over time. Per unit time now, okay? And you can substitute your energy equation up there. You will get power equals to VIT over T. So at the end of the day, you have P equals to IV. This is the main equation where you will be calculating your power. But of course, there are other methods for this, but hang on a second. We write down the unit. Power is also a unit. This one, the unit is watt. What is the unit? Watt. What is the unit? Watt. I just said what? Watt. There are other forms of this equation. I'm going to write a few of them. Remember, we have, what are those called? Ohm's law. So recall, Ohm's law, V equals to IR. Sometimes you may not know the I or you may not know the V. Then you cannot use this equation already. You have to use a different form of it. So one form is, let's draw here, this form. If you substitute in, what shall we substitute in? V equals to IR. Okay. Then you will get P equals to I square R. That's just another form of it. Now, if you substitute in, what else can we substitute? I. Let's substitute I. So if we rearrange, then I will be V over R. Then we will get P equals to V squared over R. They're all different versions of the same equation. So make sure you know which one you want to use or which one you have information for. So this and this as well. 3 forms of the power. You say, Miss, then we can substitute into energy also lah. Yes. Substitute VIR, you get 3 forms of the energy equation. All the same. So when we talk about power in terms of a circuit, okay, usually there's a few power that you can talk about. Let's draw it out. Let me say there is a battery, internal resistance. Oh man, here we go again. Oh, this is a very big circuit. Okay, it's alright. We'll draw it out. And we have a light bulb, for example. Okay, why I draw that line? So when you use, let's use power. When you want to find power, you need to know exactly what you're plugging into the equation. So let's say you want to find what is the power dissipated. Okay. Power, the keyword is rate of energy, okay? So power dissipated by the light bulb, for example. Light bulb has current flowing through it, so it will light up, dissipate electrical energy as light. So here we can say, in terms of the light bulb, power is the rate of energy converted or dissipated. Or converted from electrical to, I don't know what other thing, light and heat. Okay, so we say light or heat. Light and heat. So if you want to plug in your values, you will need to know what's the resistance of the lamp, or at least the potential difference across the lamp. Like this. V. This is number 1. Okay, what if you want to find rate of energy provided or rate of energy generated using the EMF? So this EMF got some energy happening here. So if you want to talk in terms of the power of the battery or the power of the EMF, then you have to do this. So in terms of power generated by the battery, this will be the rate of energy also converted lah. But this time, it is from chemical to electrical energy. And if you want to actually calculate what that value is, you have to use P equals to IV. Or in this case, IE, because E is the EMF. You cannot use the other two forms. Why? Because EMF does not have resistance. Cannot use. Don't have resistance. Cannot use. Okay. So we cannot use all the thing. The other one down here we can use P equals to IV lah, or P equals to I square R lah, also can, or P equals to V square over R, also can, as long as you have enough values to calculate. But EMF only can use this. One more that they may ask you sometime is, I don't know, potential difference also can, right? Sure. So you can ask about terminal potential difference. And then you have to say the power supplied to external circuit. This time you will use P equals to I times V terminal. Because you want to use resistor, a bit weird leh. The thing you know for sure is current and V terminal. So that one's what you can use. One more you can add. Okay, let's use the last one. What if you have lost volts? Very hot, right? See the heat coming out? This is the V lost. And this one, you would call it as power dissipated or power lost in the battery. If you want to calculate, how to calculate? This power is only for internal resistance. So you could use P equals to I times R. Or you could use P equals to I square R, sorry. Or you could use P equals to I times V lost. Or you could use P equals to V lost square over small r. This one all also can use. Okay, make sure you know which power you are finding. So many power leh. How to know which one? You slowly read the question, okay? You must know. Alright, one last thing to note is the lamp's brightness. Side note. Power is related to the lamp's brightness. Lamp brightness. So if they ever ask you to compare the brightness of lamps and how it changed, you need to talk about power. Oh, which lamp is brighter? You go and count which power is greater. Oh, did the lamp get brighter or darker? You go and check the power, how it changed. which equation you use, you have to see carefully which situation you have enough information. And of course, consider carefully, is the lamp in series? Is it in parallel? Where's the thing we looked at just now? In series, you need to know what is same, what is not. If it's in parallel, what is same and what is not? Compare carefully. Choose your power equation to compare. Make sure if you want to compare power, choose the equation that has more constant. So for what does that mean? So let's say Pi square R. Let's say I is constant. So then I can conclude P proportional to R. If you have greater resistance, you have greater power. That's only if I know I is constant through or comparing between two values. So the only thing there for you to do now is go try out some past year questions about power and energy and analyze circuits very carefully. So that's all for this video. I'll see you in the next one.